right, I guess it's time to get started. Just want to share a few things with you from the previous class, the cisp300 class, Introduction to Computer Science. We did not talk about anything that related to the textbook, unfortunately, in that class, and instead we talked about the Google Glass project, which was fun. I think it's a good segue into this class because, well, let's think about what something like that can do, the Google Glass project. I'll go ahead and bring up their webpage, Google Glass project.
I'll show the skydiving video from Google I/O.
Okay, this is the wiki part. Do they ever show the projection, like what a user can see, out of the glass?
There's no.
Oh, there's
nothing on what the user sees yet.
Okay.
So the glasses have.
It's just it's just video.
Yeah, and then there's an overlay. So projecting over your image can be data.
So
Yep.
it's the glasses version of the HUD.
Yes.
Yes, basically, it's a very lightweight, HUD. But I think there's a lot of potential for devices like this. Let's imagine what in terms of hardware is doable already. Okay, so I'll start off with a discussion of how would you like to type your 7-page English paper on a device like this. Let's say I give you a hexa-core device, but still with a screen like this size, but it's 1080p. Would it help?
What's dictation?
It wouldn't be very helpful, right? I mean, even with eyes like yours, because you guys most of you are younger than I am, so you'll be able to see, details a little bit better than I can. But even with your eyes, 1080p on a small screen like this is really not going to be very usable because, your retina only can pack so many pixels, per square inch, on your retina. Okay, so what a Google Glass or something like this, I'm not endorsing the product from Google, I'm just talking about the concept. What if, let's use my own glasses as an example. What if I can project an overlay computer display on top of what I'm actually seeing? Now think about that. But that means I would have to pack a 1080p projection system into a tiny little space. Is that possible today? Can I pack that many pixels into a very small tiny device? The answer is yes. We don't have any problem packing pixels into a tiny small device. We have problems seeing it because our eyes can only see things at a certain resolution. But with a small projector, I can go through optical systems to project 1080p over maybe 75 degrees of my visual field. 75 degrees is about the wide angle width of a 24 millimeter lens back in the 35 millimeter days, which is fairly wide. Okay, it's not as wide as your entire vision field, but it's wide enough that your what you focus on is already it captures everything that you can focus on. So just imagine that. Okay, one for the left eye and one for the right eye. Now you get 3D vision automatically, right? Because you can now play all your games in 3D because each side has its own projector. It doesn't have all the flickering problems and refresh problems with a 3D TV because it's not trying to share the same screen with two different visual fields. It is one projector per side. Now think of let's say we have this device. It's already pretty cool because you can let's say you can communicate with your cell phone using a wireless technology. So now your cell phone screen is irrelevant because everything can be projected onto your visor, or your HUD if you want to. So now you can watch movies in really 1080p, plug in your headphones. You don't need to go to the theater anymore, unless you miss the smell of popcorn and sticky floor and people kicking the back of your chair. Right? I mean, that's usually what I remember when I walk out of a theater, not the content of the movie. Or kids screaming, people walking past you to the bathroom and back, and then go back and buy more drinks and then back again, and then go to the bathroom again and back again. That's why I usually pick the middle seat, in the aisle, so that people would just kind of go in both directions, off of me, not over me. Okay, now on top of all these features, let's add 2 cameras onto my visor. Okay, again, the question is, do we, technologically speaking, can we make cameras small enough that we can put 2 onto the frame of my glasses without weighing it all the way down?
Yes.
The answer is yes, okay? And how about the resolution of that camera? Do you think I can fit maybe 720p at least? Easily, very good. What about something like Kinect? Like a wearable, portable Kinect that projects, that sees out of my face and not into? Okay, that's possible. Now, so all of these pieces of technology are already in place. We already have the technology. What can we do with this technology? What do you think? Now, this Google Glass, I think, is only it can only receive and record. I think, does it have an overlay too?
Supposedly. But
Supposedly, okay. So in time it will. So let's say we have all this technology packed into the size of my eyeglasses. What are we going to do with it?
On-the-fly translation.
On-the-fly translation, okay, that's one. What about your 7-page English paper that we were talking about? Do you think you'll be able to kind of type up the English paper using this device?
Yeah, sure.
I think absolutely. What about the keyboard? I mean, it's just a projection thing. Your keyboard is virtual because we have the Kinect or 3D vision capability. So what you can do is it can project. Now the camera can see this surface, my podium, and therefore it knows the distance from my face to this thing here, and it'll be able to project a virtual keyboard on this particular surface. When I type, when I move my fingers, it'll be able to track the movement of each individual finger. And therefore, when I do a virtual type on the keyboard like this, it'll be able to figure out what I'm typing. So typing a 7-page English paper will be pretty easy. But where's the pointer? Where's my touch screen? I don't want to touch my eyeglasses. That's going to put some smear on my eyeglasses, right? It can track my eyeball. It can first it can track my head movement. That's not difficult to do, but it can also track my eye movement. So that means combined with my head movement and the eye movement, it can actually know where I'm looking at on the virtual screen. What about clicking? No, blinking would be kind of dangerous, right? I mean, I can click the wrong spot depending on when I blink. Yep. Any ideas?
Same as the virtual keyboard. Just have a spot near the keyboard that interprets.
You can use a virtual keyboard. One particular place is your key for the click. There are other things. You can just make a tongue click sound like. I can imagine a class like that. Everybody's clicking. It's like stop, because you're clicking my keyboard. My microphone can pick up your click, right? That would be bad.
That's why it would have to be subbed locally.
All right. Why is it not happening yet?
Saving money. Just walk over.
Saving money? Well, no, people are willing to pay for that. Sorry, go. Okay, go ahead.
We don't have a strong enough battery for it yet. It can't hold the charge. It doesn't hold the
It can be tethered. I mean, you can. There are ways to project power using inductance. You can also have a very thin wire from the back, to let's say a neck thing. So there are ways to make that work.
Solar on the sides. Sides of the frame, you could have solar paneling.
You can have solar panel on a baseball cap, for instance, or a hat of some kind, or propeller head, the proverbial propeller head. Instead of having the propeller head actually doing nothing, it's a wind turbine generator. Okay, Okay, so we are talking about technology is almost ready for something like this. The missing part is, go ahead.
I was thinking that maybe they have newer technology that they want to release before they release stuff like that.
Well, that's potentially a reason, but I think the biggest reason is, yes, go ahead.
What the intended purpose is for those glasses, who it will benefit, what industry, maybe that'll be.
I think everywhere you look, literally, you will find benefits. Let's say you're driving, okay? Now, when we're driving, we use, some people use the GPS to take them everywhere, right? But where do you put your GPS when you're driving?
Away from
On your lap? No. you put it on the windshield or somewhere, but it's still distracting. You still have to kind of look at the GPS and then keep driving. With a device like this, it can project a virtual image on the road itself, and have a virtual right turn arrow where you're supposed to make a right turn. Yep.
I read an article that they're actually might be putting that into actual car like windshields.
Yeah.
Like an actual GPS.
Yeah, but this stays with you all the time. So even when you're walking, you can still get GPS location and whatnot. The limiting factor, and which is the part that relates to this class, is what? We have all the hardware. The hardware is not the issue.
Software.
The software, exactly. The software is the issue, okay? Because you need all kinds of software to do all of this work. Okay, it's the same reason why we don't have cars that can drive itself. Do we have high resolution cameras? Well, yes, but it's not common. Okay, it's not common because the technology is not quite mature yet. Okay, but even if you look at a Google car has all kinds of extra equipment to make it work. It has a LiDAR, LiDAR, which is it works on the same principle as radar, except it's IR based, infrared based instead of radio frequency based. But it's still the same technology. It's really kind of tedious because what happens is it shoots out an infrared beam, in a sweeping motion, and then it will look at the reflection of each point and use triangulation to or either time of flight or triangulation to figure out where that point is, and therefore it can paint a 3D picture of your surrounding. That's really old technology. Do we have LiDARs when we drive? We don't have any LiDAR. We have 2 eyes. That's it. So how can we drive with 2 eyes, but a Google car, which is supposed to be like top of the line and high technology, still require all these different technologies mounted on top of it just to drive safely? It's the software, okay? Because you cannot just mount 2 cameras on a Google car and expect those 2 cameras, potentially with a mount that can also rotate and swivel and whatnot, to do the same thing as you and I can do. So it's all software. And that's why I think the future is very exciting. I think it's going to be limited by software and not hardware so much anymore. It used to be a lot of the limitation is on hardware because we could not pack projection technology, processing power, and so on and so forth into a tiny package. Let's say even 30 years ago we could not do it. It's just impossible. But now we can pack all of that stuff, it's the semiconductor, the hardware stuff, we can pack it all already into a manageable size. Maybe not as small as you want it, but it's manageable. Yep. Okay? But it's the software that is missing. In other words, the big, huge, patent wars between Samsung and Apple is really a battleground for dinosaurs. Because what are they battling over? The 2-finger, the pinch, zoom, motion thing. It's all going to be gone, by the time we move on to a HUD type of interface. I think we will all live to see that. I mean, within the next 5-10 years, I think we'll start to see that becoming more commonplace.
Apple and Samsung are both losing out of this.
Yeah, Apple and Samsung will still be at battle with it because they would just fight over some silly idea of But I'm using double blink as double click. You cannot use that idea.
Samsung provides the screens for their Air with the Mac Air books, and then there's safe.
Or they will fight over something as as simple as But I would use a wink to represent right click.
Make a fist for the Apple key.
There's a cool image if
You cannot use that concept because it's my idea. It's a novel idea that has never been done before. Using a wink as a right click. Yep.
What if a person has a facial nerve disorder?
You train the program
keeps
then.
winking all the time.
You train the program and say, no, that is not what I meant. If you train the system enough, with neural networks, which is a type of AI, that you can train software, almost the same way you can train the person. Same thing with voice recognition. I was joking in my previous class, with voice recognition, they're already fairly good, in terms of voice recognition, and some can even handle, accents, because you can train the software. You can basically say, okay, I have accent, this is not what I said, this is what I said. Okay, you can actually train the software to recognize, what you're saying. But if you push this, analogy far enough, we don't need to talk, we can just grunt, right? Because as long as the computer can differentiate your grunts and say this is is blue and is red and so on and so forth, if your computer can translate what you grunt into the concept that you want to represent, it can now it has a universal language to communicate with another person. Okay, because by the time it gets to my end, it will just be grunting the way that I understand red and blue, right? So individual language, the convention of using language, for society, can even disappear, when software gets to the point where it can interpret what you want to communicate without having a common base of a language.
And then we'll get a big cube, fly around and assimilate.
We'll be grunting chimpanzees, that's what we'll be. With big guns.
I'm the cutest of four.
All right. So enough digression. I just want to bring this up because I think there's a lot of software work to be done. Even with existing feasible hardware, there's a lot of software to be done. Unfortunately, the patent wars is just it's just throwing a wrench into the big engine. Slows down everything. Developers are very creative, or creative people can hire developers to implement a lot of concepts, ideas, experiments, and so on and so forth. But the lawyers are suing everybody, even if there's no ground, they can still sue, right? If I'm Apple and you are an individual and you have an idea that I really like to steal, okay, how do you think I would go about doing it?
First try it.
I'll just keep
Buy
suing
it.
you until you say uncle.
There you go.
Right? Because I have a whole army of lawyers, who need some work to do, and you are an individual who needs to work to make a living. So if I can just draw out the lawsuit long enough, you will have to lose. Even though I have no ground to win, you will still have to lose. So unfortunately, that's basically stopping a lot of innovation.
Did you see the magazine ad that has the built-in LCD screen? It's an Entertainment Weekly. It has a circuit in between two heavy pages is a circuit board. It's actually an Android circuit board and an LCD screen, and it has a T-Mobile SIM. And so as you're looking at this magazine page, this live Twitter feed is coming through on the page.
Okay, that's cool.
An ad. It just blows me away.
Well, I mean, things are progressing a lot faster than it used to be in the past of decades. Yep.
There's actually a cool image you can search for that shows the current patent wars, and it has arrows going between it. Really, it's kind of an interesting thing to look at how many different companies are not only suing each other, but also helping other ones that they're suing with suing other ones. So intertwined, it's crazy.
It is. And what I think can happen is individuals like us can start to document our ideas and concepts. So these companies cannot patent those concepts and ideas anymore. Right?
Yeah.
Because they can only patent something that is novel and new and has never been done before. Anyway, so let's get back into software and the homework. Remember the pre and post condition homework? So what I'll do is I'll first take a look at the turn-in rate. Oh, I just logged out. I did not intend to log out. So we're now getting back to stuff that we have to do.
That's not fun. So that's not fun.
That's not fun.
That don't want to share.
Okay, we have 27 people who turned in, so that means that a bunch of people did not turn in. What I'll do is I'm going to postpone the deadline of this homework assignment to next Tuesday, because I don't want to give people bad grades or low grades. I want you guys to know how to do it and turn it in with good submissions. So what I'll do is I'm going to change this. and postpone the due date. People who have turned it in already, don't worry, it is still good. I'm not going to change the assignment. I'm just going to talk about it again today so that everybody knows what to do with this homework assignment. What is next? Oh, okay, never mind. Okay. First of all, let's talk about the concept of pre and post conditions. Why are we doing this? What is the purpose of the whole thing about your pre and post conditions? Because, okay, you ready? Okay. Because before we work on this, to work on all the details, it is the most important part is to understand why we are doing this. Because without understanding why we are doing this, it's really hard to differentiate pre and post conditions from tracing. So what I'll do is I'm going to try to write down as much as I can so that this will be documented. And I'm going to use a folder for today. Make sure I save the file first. Okay, any questions that I can answer? Hello? Okay, yes? Yes, if you have turned in something then you want to resubmit something, yes, you can go ahead and resubmit. You do not have to resubmit, whatever you turn in is already in the system, so you're good to go if you do not want to turn in anything different. All right. So what I want to do is to talk about what is the difference between tracing an algorithm and working on the pre and post conditions of an algorithm. We'll work with something that we are very familiar with and use that as a starting point. It may not be exactly like this, but it's close enough. Because all I want to do is to illustrate the concept, why we are doing this, and not necessarily just this particular example. Do we recognize this pseudocode? Yes. Okay, it finds the maximum of 2 variables and store the maximum in Z. We have done this many, many times. The first approach to look at this algorithm and try to figure out what it does and get an idea of how it works is to trace it. Okay. Now, when we trace an algorithm, we have to do something like this. I can do a simple trace without using a spreadsheet because I can just say, comments is 1 column, line number is 1, X, Y, and Z. They're 1 column each. But in order to trace an algorithm, I need X and Y to have specific values because otherwise I would not be able to actually walk through the paths. So I need X to have a particular value, Y has another particular value. Then I have to trace the program line by line. I start with line 1. Line 1 has to evaluate a condition. X is less than Y is true in this case. And then based on the logic of the program, I have to go to line 2 and not line 4 because these specific values in X and Y tells me that I can only use the then branch and not the else branch. So on line 2, I will do one thing, change the value of Z to become the value of Y, which is 5. And then I'm done because I'm out of the conditional statement, and I use post to indicate that I'm all done. At this point, I can look at the result of the trace, and I can convince myself one thing. It works in this particular case. When X equals 2 and Y equals 5, it does find the maximum of the 2 and store it in Z. I have no idea whether it will work when 2 values are exactly the same, or whether it will work when X is greater than or equal to Y, and so on and so forth. I can only prove that in this one particular case, it worked. I can go through different traces. Okay, I can give it 20 gazillion combinations of values of X and Z, X and Y, and prove that in each case it works. But it still doesn't give me any confirmation that the algorithm is correct. Are we doing okay so far with that concept? Traces are good because it gives us an ability to walk through a program using specific values in the variables. But it doesn't tell me conclusively that the algorithm is correct and it will work regardless of the values of x and y. Are we doing okay so far? Are we understanding the limitations of tracing a program? Okay. Now, when we work on the pre and post conditions, it is a little bit different. Pre-1 is a condition that is guaranteed when the algorithm starts. In other words, in this case, I may not want to say anything at all. I can say, well, I don't need to know anything about x or y when I start this algorithm. Other times, you might have restrictions on the input of an algorithm. You might say, oh, let's assume this array is already sorted, because this algorithm only applies to sorted arrays. So you might want to put some additional restrictions depending on the algorithm itself and see what it requires. That's the precondition of the entire algorithm. Are there any questions about in terms of pre and post conditions? What is the meaning of the precondition of an entire algorithm? Not only of one line, but the entire thing. It's just a guaranteed condition and say that you can make assumptions like this before the algorithm starts. In this case, for this particular algorithm, I say, oh, the precondition of line 1 is simply true, which is the simplest condition that is guaranteed to be true. Right? Okay. So this means we don't need to assume anything about x, y, or z before the algorithm executes. But in some other algorithms, we'll see later on, we want to guarantee some sort of conditions, like an array is already sorted. I'm not going to go through the derivations because we have done that already. I don't want to waste the time to do it. But I want to do something about post 5. I don't care about the details of post 5, but what does that mean? Yep. It's post 2 or post 4. I don't even care about that part. But what is the meaning of post 5 from the perspective of the algorithm? Yes, go ahead.
It's after the entire thing is done.
Yep, exactly. Post 5 is a condition that is guaranteed to be true. Okay, the other one I can also make it more redundant. Guaranteed to be true when the algorithm finishes. Because we only have 5 lines here, so post 5 is the end of the entire algorithm. So this is a condition that is guaranteed to be true when the algorithm finishes, assuming that we start with pre-1 as a precondition of the algorithm. Now that is a very powerful statement because it is basically saying if you can guarantee that this is true before the algorithm starts, I can now guarantee that this has to be true when the algorithm finishes, regardless of the values of x, y, and z. As long as the values of x, y, and z can make this true, I will make sure that this has to be true when the algorithm finishes. Are we understanding the meaning of pre-1 and post-5 with respect to the algorithm? Not the details or the derivations, just the concepts. What do they mean when we talk about an algorithm? One is a restriction of the input. The other one is a guarantee of the output, assuming the input restriction is met. Okay? Are we still doing okay so far with this? Okay. If we can match post 5 with what we think the algorithm should do, then we just proved the algorithm is correct. Remember the long exercise, that we were trying to do the other day, like 2 weeks ago? I gave you post 5, but I also expressed, what the output is supposed to be. We didn't quite finish that exercise because it requires a lot of Boolean algebra to do all the manipulations, so I didn't finish it. But assuming that I finished that proof basically says, regardless of the input, as long as it makes true true, post 5 is guaranteed to be true as well. And because post 5 matches a description of what the algorithm should do, the algorithm is now correct. I have just proven this algorithm is going to do the right thing regardless of the initial values of x, y, and z. Can everybody see how this approach is different from the tracing approach? Okay. The tracing approach is a one-shot thing. This one is universal. Are we doing okay so far? Okay. Now, if this is okay, then we'll go ahead and start with an example. I can start with something like, if x is greater than y, then if y is greater than z, then we'll just go ahead and say k gets k plus 1. And if this is just an example so that I can show you, how to do the derivation. All right, so here we have an algorithm. And pre-1 in this case is just a guaranteed condition before we start with this algorithm. Now, I can base, as an example, I can say anything I want, because in the end, all I'm trying to do is to relate pre-1 to post 5. That's all that I'm trying to do. So pre-1 in this case can do something about, we can say 2 times x is greater than another variable w, which does not even appear inside the algorithm itself, but it's a variable sitting somewhere else, and I can say that 2x is greater than w. And I can say something that is totally unrelated to the stuff that I'm doing here. I can say k mod 2 does not equal to 0. K is basically an odd number. Is that disturbing a little bit outside?
Yeah.
I'll go ahead and. I'm not going to take my
Oh, it's called RAND, which is a law that says that you have a game-changing patent, you have to share.
Better?
You can expect compensation. It has to be fair.
Pass the roll.
And there's a lot of
Roll sheet for today. Okay, so getting back to the pre and post condition stuff, pre-1 in this case is simply saying that every time I run this algorithm, I guarantee you that 2x is greater than w, and k mod 2 is not 0, which means k is it odd or even? Is odd, right? Because k divided by 2, has a remainder of non-zero, so that means it has to be an odd number. Okay. That's basically all I'm guaranteeing. This is something I can guarantee you. I want to see what you can tell me about post 5. In other words, if I start with this condition, if I can guarantee this, what can you guarantee after the algorithm completes? That's the question. Yep.
You would be able to guarantee that pre-1, the 2 times x is greater than w, and k mod 2 is not equal 0.
Well, Not all the time. It depends on how we are going to. So that's what we're trying to do next, is to work this out step by step, so that we can come to a conclusion and say, by the time we get to line 5, when we're done with this algorithm, this condition, whatever it is going to be guaranteed. Okay. All right. So we'll work on this, step by step. There's no such thing as a post 1. I would not name it post 1. Instead, I would call it pre 2. Now, this is already starting to become tricky, because this is a conditional statement, but there's no else. You can see there's no else to either of the conditional statement. So what do you think I should say about pre 2? Okay, pre 2 is going to be whatever in pre 1 still has to be true before line 2 executes. But in addition to that, I also can be guaranteed one more thing if my execution path is on line 2, because it means that the condition of the conditional statement, starting with line 1, has to be true. It really helps if you want to draw a picture. This really helps, because what happens is we have a conditional statement. We know a conditional statement has a branch. And with this branch here, we're asking this question: x is greater than y, is it true or is it false? That's the question. We label the 2 branches. One is labeled true, the other one is labeled false. This part is universal to all conditional branches. Okay, you can have different stuff attached to it, but the branch or the fork is guaranteed. Okay, are there any questions about this? Nope. Okay. Now, if we do follow the true part of the branch, that means that is line 2. What is line 2? Line 2 is the beginning of another conditional statement. Okay? So we have another structure similar to the first one, but it asks a different question. Y is greater than z. Is it true or is it false? Are we okay with the picture so far? If it is true that y is greater than z, I'm going to update k, so k gets k plus 1. Now I can finish the whole picture. The entire thing, okay, the inside conditional statement, line 2 to 4, will have to merge first. Okay? Well, that's the nature of a conditional statement. After you branch, they have to merge. The only thing that makes this a little bit different from all the other conditional statements that we have looked at is the else branch has nothing to do, which is the same as saying x gets x plus x times 1. Does that sound vaguely familiar to you? If it does not, we have a problem. Because it's in the homework. And then these 2 will also merge into one single branch out of the entire algorithm. Are we doing okay so far with this picture? Pre 1 is basically saying, by the time we get to this point, I can guarantee you a particular condition. And that condition turns out to be this pre 1 on the projection screen. 2x is greater than w. Don't ask me why, it's just guaranteed at that point. And k mod 2 is not 0. Don't ask me why again, it's just guaranteed. My question is, given that is a condition that I can guarantee you, what can you tell me at the end of the execution of the entire algorithm? What is guaranteed at the end? Sorry? Pre 1? Not necessarily. It was pre 1 with some other stuff, right? Okay. So we want to work on this, step by step.
Is it post 5?
It is post 5. Yeah, this part is post 5. Do you guys want me to remove the podium? Because I think it's blocking the view of some of that stuff. Okay. Let's do this as quietly as I can. Oh, that's not good. Okay, there's a lot of stuff in it, and the bottom piece is not there. Just fell off.
That was very nice. Looks like I can't remove from the podium.
I don't know why we have a podium.
Nice to go to my soapbox.
All right. Well, I can't really remove it then. You know, the bottom part is just a merge of all the branches. Is that okay? So all branches, there are 3 branches. This one, and this one, they all merge at the end before it exits. Is that okay? I mean, I'm sorry that I cannot, remove the obstruction here. Nor can I scroll the screen.
We'll just call that post 5 where they all merge.
Yes, after they merge, it's post 5. Okay. All right, so we'll work on this, step by step. The first step is to figure out not the post 5, but just to figure out this part here. Okay, if I get to this point here, what can you guarantee? The only thing, and I'm not going to tell you exactly what are the values in x, y, z, and w. Well, let's think about it. In order to get to this point, I have to come from this point here. So this is pre-1. Did I have a chance to change anything in between? No. There are no assignment statements in between. So pre-1 still has to be true at this point. Right? Whatever it is, it can be as simple as true. It can be as kind of senseless as what we have here. But whatever pre-1 states still has to be true after we decide to take the true branch. But something else also has to be true. What else? X is greater than y. X is greater than y. Because this is the question we ask. We took this branch, so we know that x is greater than y is also guaranteed to be true when we are here. Are we doing okay so far with that? Okay. This condition, in return, becomes the precondition of the inner conditional statement starting on line 2. So I don't really have to say anything about this part here because it really is the same thing. We don't have anything else to do. But we do have something to say when we get to this point. This is what? Pre-new. Yeah, it is pre-3. Sorry. Pre-3. This is the precondition of line 3. Right before we execute line 3, what do we know? Well, we know that whatever is in pre-2 is true. But we also know one more thing. Because we decided to take this branch, we also know that y is greater than z. So y is greater than z is also guaranteed. I'm not going to expand it here because it just takes more time on the whiteboard to write it. But you do have to understand how this pre-2, which is here, is related to everything else. So I'm just going to write pre-2 is this, and this is pre-3, which is this part here. Are we doing okay so far with this? Okay. Now, if you look at just this portion of the entire picture, just this portion here, whether it is inside the conditional statement, does not matter. Because the next step we want to do is to say, okay, now that we know what is pre-3, can we figure out what is post-3? In other words, this is post-3 here. Do we have any method to go from pre-3 to post-3 when line 3 is an assignment statement and it is reversible? Yep. Use the substitution rule. Okay, so you have to figure out what is the function f, what is the inverse of that function, and then apply the substitution operation, and that will give you post-3 here. Are we still doing okay so far with the concept? Okay. Now they all merge, right? Well, when they all merge, we kind of have to think about the condition for this part here, which has no particular name in this example. It has no particular name for this example because it simply represents, a else branch. But we'll go ahead and figure out what it means to be on this side.
Z is greater than or equal to y.
It is, well, okay, we still have pre-2 being true. So pre-2 being true goes all the way up to here, but now we have to take this branch, which means pre-2 is guaranteed to be true, but at the same time, y is greater than z is guaranteed to be false. So we'll just simplify and say y is less than or equal to z. Are we doing okay? What about this guy here? It also does not have a name because there's no particular line corresponding to that branch. But what can we say? Pre-1 still has to be true. Okay, pre-1 still. And what else?
X is less than or equal to y.
Yep, x is less than or equal to y. So now we have figured out all the branches before they merge at the very end. We have this branch here. Okay, so I'm going to use blue. We have this branch here. We figure out what it is. We have this branch here. We figure out what it is. We have this branch here. We figure out what it is. They all merge at the very end. At the bottom of this picture, they all merge. So standing right after the merge point, what can I say about the condition at that point? We are guaranteed that at least one of the three has to be true. Okay? It's just a simple OR. So that way we say at the end, we say post 3 or pre-2 and y is less than or equal to z, or pre-1 and x is less than or equal to y. So let's go ahead and write it out and then actually go through the derivation in this case. But it's all based on the picture. The picture is more important because it gives you a visual display of how the pre and post conditions relate to each other. But this part is really just the tedious part because for the most part, what I'm doing here is copying and pasting until we get to the substitution. Pre-1 is just this whole chunk of stuff, and then we just copy and paste the other part, and that gives us our pre-2. Are we doing okay? Are we relating what we have in the text editor with the picture? It's okay? All right. And then for the same reason, I can talk about pre-3, because according to this picture, pre-3 is pre-2 and y is greater than z. So I'll just write it out like this. And then I'll do the expansion. Now when you do your homework assignment, you should do the same thing here. In other words, you should do it step by step and not skip one step. The first step here, I'm just going to highlight it. This step is determined by the structure of the code. The second step is more trivial because it is just an expansion of what pre-2 is. So I'm just expanding what is pre-2 so that I can work with this later on. Now when we want to talk about post 3, we want to talk about line 3. So we'll say f of k is k plus 1 on line 3. And there is an inverse. The inverse is k f prime of k. And since we're just adding 1 on the right-hand side, to undo that, we just have to subtract 1. Yep.
For the first line of 3, too, the 2 times x is greater than there also. Like it's supposed to be 3 is equal to 3, 1, and x is greater than y, and 2 times x is greater than w.
It's here. I expanded pre-1.
Well, it's like simplified, but you have to put on the first line too, or just like that.
Could you ask that question again?
Like you have to have the 2 times x is greater than w in that first one right above that one before you change it.
You mean here? Yeah, the first line is because of the structure of the code, and then the second line is expanding what is pre-1 so that I work with the actual condition.
Okay.
All right, so now that we know there's an inverse function to the function on the right-hand side on line 3, we can determine that we can use the substitution rule. The substitution rule is actually very simple. It's very mechanical. The post condition of a line is based on the substitution result of the pre of that line. We take all occurrences of the variable on the left-hand side, which is k in this case, and replace every single instance by the inverse function applied to k. So you always have to start with this part here because it relates the precondition to the post condition. It also put the inverse function into it so that now we have all the pieces in. The next line, when you do your homework, the next line is to expand what is pre-2 or pre-3 in this case. So I'm just going to copy and paste here. You don't have to really copy everything. It's really quite mechanical. So you don't need to do that part. Just say you expand what it is. And then we maintain the k here. And then the inverse function is k minus 1 in this case. And then the last step is to apply the substitution. In other words, we just look at this entire thing here. And then we say, every time we see a k, we'll replace it with k minus 1. There's only one place. This k gets replaced by k minus 1. The rest of the expression does not change because they only contain variables other than k. Are we doing okay so far with this exercise? Okay. So now that we have post 3, we have to figure out the other 2 branches. I don't really have a name for those because they really do not correspond to any specific line. So what we'll do is we'll I can write it like this: the condition, of the alternative branch to line 3 is going to be pre-2 and y is less than or equal to z. In other words, in the inner conditional statement, if I did not go for line 3, the alternative condition that is guaranteed is pre-2 and y is less than or equal to z. Are we doing okay so far with this? Okay. Now at this point I can actually say something about post 4. Because according to the pseudocode, post 4 actually has a significance because that's the merge point between this branch here and also this branch here. Because they merge first, and then they will merge again with the other branch. So post 4 actually has significance here because post 4 is basically post 3. Oops, I typed in the wrong place. Because it's basically post 3 or the alternative path, which I will just copy and paste here. Are we doing okay so far? If you look at the picture, we are looking at the first merge point down here. Let me see if I can remove this more carefully so I don't drop everything. Oops, sorry.
Just a few things.
Whoever is going to put it back up or need to access the stuff inside is not going to be happy because it's all going to be shuffled. All right. Is that better? Can you guys see the bottom now? Okay. So post 4, what we are working on right now on the whiteboard, is basically this part. It's the first merge, right after the first merge. So I'll just write down here. Just pick up the pointy objects before I step on it. Are we still doing okay? All right. And this becomes a little bit complicated because post 3 is a fairly complicated expression already. But that's okay because I have the editor and you don't. Most of you don't. So you have to just write down the approach. You don't have to copy down everything. I mean, this is just a lot of details. Right? I mean, there's no need for you guys to copy everything on the board. Okay? And this is going to merge one more time.
Well, shouldn't you expand pre-2 as well?
Oh, yeah, you're right. Let's expand pre-2, which is up here.
Ridiculous.
There's a lot of common stuff. You can actually factor out the common stuff. Like x is greater than y can be factored out just because of the distributive law. You can actually take things out, but it's not worth the effort at this point. Okay, what is post 5? Post 5 is down here. This is the last merge point. So that means we are trying to figure out this part here. Post 5 will include post 4, but it also includes the condition of the alternative path to the inner conditional statement. So I will need to state something like this. Condition of the alternative branch to lines 2 to 4 in this case is the following. The following is going to be pre-1 and x is less than or equal to y. Are we doing okay so far? I'm just relating what is on the picture to just text. Are you still doing okay? Yep, go ahead.
So the alternative branch is the false path, right?
Yeah. Instead of executing line 2 to 4, we would have taken the other path. So the question is, what is the condition guaranteed when we go to the alternative path?
And that's when we make y less than or equal to 0.
Correct.
Okay.
So now we can talk about what is post 5. Post 5 is post 4, or the alternative path to lines 2 to 4. So we'll copy and paste it here, and then we'll expand post 4. Post 4 is already kind of long and cumbersome. You can see how I'm going to do this part, right? So I'm going to take post 4, which is this big chunk here, and then just stick it down here. I'll do the formatting later. And then this part is pre-1 and x is less than or equal to y. And then we'll go ahead and copy and paste what is pre-1. And then reformat everything so they look about right. I have to use indentation within parentheses. That's bad. Right? Am I missing anything? And this is a good,
This
segue.
is just a simple little 4-line thing. If you had
What?
thousands of lines of code, this would be impossible.
Exactly. That's a very good point. It's a good segue to talk about that next. I mean, I am sorry, but I just have to make this look right to me because I cannot stand stuff that is not indented correctly. Okay, I'm missing something here. Okay, I'm missing this part. I used to program in Lisp, so I should be familiar with this sort of thing. In graduate school, this is what I do all day long. Programming in Lisp, this is basically what you do all day long, is to use parentheses and match all the open and the end, make sure they all indent correctly and stuff. But basically, it looks kind of like this, okay? Okay, what it looks like is really besides the point. The question is, what does this mean? I mean, what is this junk here? After this whole exercise with this stuff here, what is so special about this condition? It's guaranteed true when this algorithm gets to line 5, assuming that you can guarantee this condition before it executes. But you didn't tell me what is the value of x, y, z, k, and w. It doesn't matter. As long as those values make this true, this result is still guaranteed. Are we doing okay so far with this?
We were until that.
Well, that's just mechanical stuff, okay? That's really just mechanical stuff. So what we want to do is to say, can we apply this approach to all programs? Because if I can apply this to complicated algorithms, then I have a way to verify the correctness of an algorithm without having to test it with a gazillion test cases, right? And that particular field of computer science has a name. Can anyone kind of guess what the name is? It's HAL 9000, Heuristic Algorithm 9000 from the movie 2001: A Space Odyssey.
No, he didn't say hell. He said hell.
HAL. Oh, okay. No, it is called program verification, automated program verification. It's also a field in software engineering. That's the original name of software engineering, is how do we write programs and guarantee the program will work the way it is supposed to. Okay, so this is a subfield of software engineering, and it also involves AI. Because what I have just done is to go through all this process manually using Boolean algebra and all kinds of rules to come to this conclusion. We want to automate this process, right? Because what we want to do is to give a program the source code of, say, Linux, okay, and a bunch of conditions that is guaranteed, and we want the program to give us an output and describe what that program is going to do and produce at the end, and match the condition at the end with what we think the program should be doing. Now think of something like this, okay? Now let's relate it to something that we have only recently started to deal with, arrays, okay? Okay, so we have pre-1, okay, for a sorting algorithm. But tag, we haven't really talked about sorting algorithms yet. It doesn't matter, because I'm not going to talk about the algorithm itself. I'm just going to talk about the pre and the post condition. Okay? So for sorting algorithm, the precondition can be simply true. I do not know how the elements inside the array relate to each other. It may not be sorted to begin with, right? Is that okay? But what do you think is the post condition of the entire algorithm? So let's say the algorithm has n lines. I don't really care how long it is. How do I express that an array is sorted? Sorry? How about this? What about this? What about a bracket 0 is less than or equal to a bracket 1? So it relates to its neighbor. And a bracket 1 is less than or equal to a bracket 2. And so on. Dot, dot, dot. And then we just have to express the last one, which is a bracket bar minus 2 is less than or equal to, oops, close bracket, less than or equal to a bracket bar minus 1. Oh, and miss one square bracket. There we go. Don't you think that will basically say that the array is sorted in a non-decreasing manner? Okay, well that's it. But what about the stuff in between here? What about the stuff in between here? A whole bunch of derivations using the substitution rule, the forget rule, figuring out the loop invariant of a loop, doing the conditional statement thing. Tedious details, okay? But what we want is to go from here and say, well, we don't know how the array is sorted to begin with, but we want the post condition to be like this. That is actually not quite how to describe a sorting algorithm. Why do you think it's not really quite how we want to describe a sorting algorithm?
Take too long?
Not exactly. I can make an algorithm fulfill these requirements just by reinitializing or changing all the values of all the elements to 0. Because if I change all the elements to 0, 0 is less than or equal to 0 is true, 0 is less than or equal to 0 is true, and so on. Everything is fine as the result. In other words, that's not a very good description of an array that is sorted. What am I missing here? Okay, I'll give you an analogy. You gave me a stack of cards, with numbers on them, and you told me and say, "Tack, sort this deck of cards so that it is ordered from small numbers to large numbers." Okay, that's my assignment. I went home and decided that's too hard. I'll just erase the number on every single one of the cards and replace it with a 0. I gave the entire stack of cards back to you and say, it's now sorted. Look, they're in the right order now. How would you like that result? What is missing from the description? Because obviously something is wrong with that description to describe what is a sorting algorithm. What is missing?
None of the values must be changed.
The values that used to be in the original array still has to be in the new array. Okay? And the number of occurrences should also be the same. In other words, if I have 2 16s in the original array, I should end up with 2 16s in the new array, in addition to the description that I have already introduced here. But how do we express that? That each value that was in the original array still has to be in the array when we are done with this. What do you think?
The sum of all numbers in the array must equal the sum of all numbers in the new array.
Well, let's take two. Let's take another trial at this. Okay. So the precondition in this case is going to be a little bit more complicated now. It's going to say a bracket 0 equals to some value that I'm not going to change. So I would just say this is a constant, k bracket 0. We have another array. And a bracket 0, a bracket 1 equals k bracket 1, and then dot dot dot, and then all the way down to the last one, which is a bar minus 2, minus 1 in this case, because it's just the last one, equals k open bracket bar minus 1 close bracket. All right. Well, that doesn't seem to be very useful, does it? It's simply relating all the elements to some other elements in another array. But that gives me an anchor point. It gives me a way to refer to the initial values in the original array. So the post condition will now have to say stuff like this. But in addition, I have some additional requirements. Because now I can say, A, there is an element in K to match a bracket 0. And the same thing for all the other elements. Okay? Is that making any sense? It's still not going to take care of the multiple occurrences one. Because if I have 3 16s originally, this doesn't describe that I have to have exactly 3 16s in the output. It doesn't do the counting. So that requires even more description. But you can see how I can try to describe the output of a program and of an algorithm using the conditions. But if I use the pre and post condition thing and be able to derive the actual condition of the output of an algorithm, if they match, then I have just proven an algorithm to do what it is supposed to. But one of the key elements to do this sort of thing is to make sure that your post condition is really describing what the algorithm is supposed to do instead of an incorrect description of what it seems to do. Are we doing okay so far? But in terms of concepts, the question is, how do we go from here to here, given a particular sorting algorithm? Let's take a look at the complexity of a very simple sorting algorithm. One of the simplest sorting algorithms is called selection sort or bubble sort. Both of those are fairly simple to understand. They're not really optimal, but they do work, and they're fairly easy to analyze. So this is bubble sort. We'll go to the pseudocode implementation, and that's it. That's the pseudocode. But inside the pseudocode, there are things that are already kind of shorthanded, like the swap here is already shorthanded because it is basically exchanging the values of a bracket I minus 1 with the value of a bracket I. So in our terminology, we will basically say, let's say this is line 1, this is line 2, and so on. We'll use our derivation method to go line by line into the algorithm, into the loop, back out of the algorithm. We'll basically say, what is the post condition of this line? Is that going to be what we think it is supposed to be? If we derive the whole thing, and this condition, the post condition of the until line, does match the requirements of a sorted array, then we have just proven that the sorting algorithm will work regardless of the input of the entire algorithm. Instead of having to feed the algorithm different test cases and hope that it will work for the next test case, I have just proven that it will work regardless. Okay, so let me ask this question again. Yep, go ahead.
So this program basically keeps repeating and switching if the top number is lesser to the bottom number until it can't do it.
It swaps only neighbors, not the top and the bottom,
Yeah.
and that's why it's called bubble sort, because the smaller values bubbles up. Every pass along this, if you look at the actual values, you can see a small value bubbling up like this, and then another value bubbles up and stuff like that. And that's why it's called a bubble sort algorithm. Are there any questions so far in terms of concepts? I don't expect you guys to understand the algorithm here because we do not have a for loop in this class. But I'm just asking in terms of the concept, do we understand what is a precondition, what is a post-condition, and what is the significance of deriving the post-condition from the precondition of the entire algorithm? Okay. How do we do this using the computer? Because obviously, if you look at this stuff here, even with a simple algorithm like this, it's a lot of hassle, and the output is really kind of gibberish. I mean, I can do some simplifications, but it's really a lot of stuff. Wouldn't it be nice if we can do this using a computer? Feed a program to another program. The second program can prove the correctness of the first one. Wouldn't that be nice? And that's what people have been trying to do for the past 50 years. In fact, new programming languages have been invented to try to make this happen. Can anyone name a programming language designed specifically for this purpose? It has to do with predicate calculus or predicate logic. No? Okay. The answer is Prolog. There's a weird programming language called Prolog, P-R-O-L-O-G, without a U-E, as a programming language. Okay. And it was a programming language invented for the purpose of deriving pre and post conditions, among other things, but it's a weird little programming language, but it's well suited for this application. But why do we still have bugs and patches, in Windows and Linux and all kinds of complicated programs? I mean, we do have the basic, mechanism to do it, but it doesn't mean it is feasible. Okay? Now, what is the difference between it's possible to do something as opposed to it is feasible to do something? What is the difference between those two? I can give you one example. Okay? There's a problem well known in computer science. It's called the traveling salesman problem. Okay, the traveling salesman problem is basically saying you're a salesman, you have to traverse, let's say, 10 cities. I will give you, the cost to go from one city to the next. So that would include airfare, time, expenses and whatnot. Okay, let's say I just give you a single number that represents the quote-unquote cost to go from one city to the next. All right? So now your problem or your quest is to figure out the best order to traverse the 10 cities that will save you, that will give you the least cost. Okay, how would you do it? Okay, let's change the problem to 3 cities. How would you do it with 3 cities? I'm just going to draw the picture here. A, B, C. How many different ways can you traverse 3 cities? Assuming you can start with any one of the 3. Okay, 1, 2, 3, 1, 2, 3, 1, 2, 3, and then reverse it. So there are 6 possible ways to traverse the 6 cities. Is it going to be too much work to figure out the cost of all 6 different ways to do it? Not too bad, right? What if I give you 4 cities? How many different ways do you? It'll be, no, it's not 8. It's a little bit worse than that. It'll be 4 times 3 times 2 times 1, right? It's factorial. We are talking about factorial here. Now, why is it 4 times 3 times 3, 4 times 3 times 2 times 1? Because you have 4 choices for the first city. But assuming you don't want to go back to the same city again, you only have 3 cities left for the next choice. Then 2 and then 1, because the last one you don't really have a choice. You have selected 3 out of 4, the last one is set. Okay? So with 5 cities, you have 5 factorial. 6 cities, 6 factorial. It doesn't sound too bad, does it? What is the value of 10 factorial?
It's over 10,000.
I'm gonna save myself some headache here and use a calculator to do it.
I did it.
Oh, okay. How many?
3,620,800.
Okay, 3 million something, right?
Yeah.
Okay. I remember one thing only. When I was, at your age, I had a calculator. It's a Casio calculator. And I remember the largest number it can represent is 10 to the power of 100. That was the largest power it can represent. And guess which factorial, what is the last number's factorial before it runs out of values? It was 89. 89 factorial, has an exponent, power of 10 of 98. In other words, 89 factorial is some number times 10 to the power of 98. And that was the last factorial that I can figure out using that calculator. So if I have an algorithm that works really well with a pizza delivery person, because how many stops do you think a pizza delivery person has?
5, 6.
Before it gets cold, right? That's the limiting factor. Your pizza has to stay warm in the truck. So maybe 4 or 5. 5 factorial is 120. It's still well within the range where modern computers can easily figure out. What about UPS? A UPS truck, how many truck stops do they have? Probably more than 89. In other words, it's going to be some number times 10 to the power of 98. Do you think, you're even with the, super duper, hexa-core, processor these days, do you think I can figure out what is the best route in general before the day is over? Before the year is over? Before the century is over?
Maybe.
Exactly. That makes it infeasible. Because by the time I have the answer, the value of the answer is long gone. The same thing applies to cryptography. Everything can be cracked with a 386 computer. The question is, by the time the code is cracked, does it still have value? The answer is no. In most cases. So that's what we are talking about, is the feasibility versus the possibility of doing something. We'll visit this again later on. Okay. So are there any questions related to the homework assignment? Did I help with the understanding of the concepts of the homework assignment? Okay.
Yes, where you can either.
Do we know what to do with the homework?
Both.
Okay. All right. I'll see you guys on Tuesday, which is also our